Good evening, everyone. Myself Gautam Sharma, and I welcome you all in a Sapience Education. For any further details, you can visit our website www.sapienceeducation.com. Further, if you want to know about more courses and all course plan, so you can also download our uh, app. A link is provided in the below description section. So today I am going to discuss about the work energy power, that is second part video. Okay, it is the second part, and already I have already discussed in the previous part. So first of all, I will start from question. So what does the question mean? It is well known that raindrops fall under the influence of the downward gravitational force. Okay, and the opposite resistive force, and the latter is known to be proportional to the speed of the drop, but is the otherwise undetermined. Consider a drop of a mass 1 gram falling from a height of 1 kilometer. It hits the ground with a speed of 50 meter per second. What is the work done by the gravitational force, and what is the work done by the unknown resistive force? So first of all, we need to understand that a raindrop is there, okay, and mass of raindrop is 0.1 gram only. So I can convert it into kg. So how I will convert it into kg? So the mass of the raindrop is equal to 1 by 1000 kg. So this will be 0.001 kg. Okay, falling from a height of 1 kilometer. So let this is the ground surface. So height is equal to 1000 meter because it is 1 kilometer. Okay, it hits the ground with a velocity of 50 meter per second. So when it hits the ground, so its final velocity is here 50 meter per second, and its initial velocity u is here 0 meter per second. What is the work done by the gravitational force, and what is the work done by the unknown resistive force? So we will apply a work energy theorem here. So what is work energy theorem? Work energy theorem is what? Change in kinetic energy is equal to total work done, that is work done due to gravity plus work done due to resistive force. So first of all, how I will find a change in a kinetic energy? So we need to use this formula to find out the work done due to resistive force. Okay, so let us put all the values here. So change in kinetic energy means what? Final kinetic energy minus initial kinetic energy is equal to work done due to gravity means what? Force under gravity into displacement, that is h, plus work done due to resistive force. So here kinetic energy, final kinetic energy, as final velocity is 50 meter per second. So final kinetic energy is what? 1 by 2 mass of the raindrop is what? 0.001 kg, 0.001 kg into v square. It means what? 50 square minus initial kinetic energy. Since body is in at rest position, so initial kinetic energy will be 0, and this is equal to force due to gravity. Force due to gravity is how much? So force due to gravity is here m into g, and finally h plus wr. So I will go for a next step. Mass of the raindrop is 0.001 kg into gravity value is 10 into height is 1000 plus burden by resistive force. So if we calculate, then how much we are getting here, uh, it will be 1000. So 5 5 are 25 double 0 divided by 2 into 1000. So this got cancelled out. So It will be 12.5 divided by 1.25. It's a 1.25. So, and this is how much? This will be 10 plus work done by resistive force, and this is 1.25. So finally, you will get work done by resistive force. Resistive force due to air friction will be equal to 1.25 minus 10. So this will be 8.75 minus. So why it is negative? Negative symbol represent direction of force is direction of force is opposite to the direction of the motion, opposite of displacement, opposite of displacement. I hope you all have understood why it is negative. Okay, so if I will draw the diagram, so we can consider this. So raindrops displacement is in this direction, gravitational force is in this direction, but the resistive force is above, air resistance is above direction. That's why work done due to this force will be negative, but work done due to gravitational force is positive. I hope you all have understood. Now I will discuss about conditions of a three conditions are there. How many conditions are there? Three conditions are there. First condition is no work is done. First condition is no work is done. No work is done. When we say that no work is done, see, and an object, let it be an object is there, and I am applying a force on this object, but the displacement is zero. So as per the formula, work done is equal to F into D cos theta. So this will be force into 0 into cos theta. So we will get 0. For example, if I'm pushing a wall, what happens here? If I'm pushing wall, what happens? If I will push the wall, then what happens? What happens? Wall does not move. So it means that work done by this person is 0. Now I will talk about case 2, that is force is 0 when block is moving on a smooth horizontal table is not acted upon by a horizontal force. Let us consider an object is here and it is moving with the 20 meter per second. Okay, no external force is applied here. It is going, no friction force is applied. So if friction force or any external force is 0, so what will be the work done? Work done is equal to F d displacement cos theta. In spite of displacement d, suppose it is your d is equal to 10, so work done will be equal to 0 into 10 into cos theta, so this will be 0 only. So this is the second case. Now I will talk about the third case. Third case is that when a force acting perpendicularly, then then the work done will be 0. Let us consider let us consider an object. An object is here and its displacement is in this direction. Suppose displacement is d, but the force due to gravity, we can take force due to gravity, that is equal to mg. Now the angle between these two is 90 degree. So work done due to gravity can be written as F into G into displacement into cos 90 degree. So force due to gravity is your mg into displacement is your d into cos 90 means 0. So this will be 0. So these are the three cases where force work done will be 0. So first is when force is applied but displacement is 0. Second is force is not applied but displacement is there. Third is what? Force is applied but displacement and the angle between These two are 90 degree. So we have got the three condition where work done is 0. So work done can be 0. See the condition, work done can be 0. Work done can be negative and positive. When work done can be 0, the case is that when cos theta is 0, that is theta is equal to 90 degree. So work done will be 0. For example, an object moving in this direction, force is acting upward. So 90 degree theta is, so work done in this case will be 0. Now case 2, when work done is negative. For example, an object is moving in this direction, so displacement is in this direction, but the force applied like friction force may be there. So friction force applied in this direction, and angle between these two is 180 degree. So cos theta is 180 degree. So work done will be equal to friction force into displacement into cos 180 degree. So we have a cos 180 degree value is minus, so minus FD, so that is equal to minus negative work done. So this is the negative case. Positive case, if an object is supposed to be applied a force F and the displacement is also occurring in the same direction, so work done will be equal to FD cos theta. So theta is 0, theta is here 0, so it will be positive. So this is the case. I hope you have all understood this all three cases. Now I will talk about one more question, very interesting. In a ballistic demonstration of a police officer fires a bullet of a mass 550 gram with the speed of 200 meter per second on a soft plywood. Let us consider there is a soft plywood and a bullet is fired by the police. Bullet is fired by the police. From here, suppose bullet is fired, okay, and its initial velocity is u is your 200 meter per second. Okay, on the soft plywood of a thickness 2 centimeter. How much thickness it is? It is your 2 centimeter thickness. Okay, the bullet emerged with only 10% of the initial kinetic energy. What is the emergent speed of the bullet? So, bullet just by making a hole, it came out, but the velocity of the bullet changes, and it is 10% of the 10% of the 10% of the initial kinetic energy. Let us consider kinetic energy of initial is 1 by 2 mv square. So that is equal to 1 by 2 into mass of the bullet is how much? 50 gram. So can I write here 50 by 1000 into velocity is 200. So can I write here 200 square? Now, the final kinetic energy, as per the question, it is saying that 1 by 10% means 10 by 100 of initial kinetic energy it is. Okay. So it is how much? So just I will put the value. So we will get final kinetic energy. So it is your 10 by 100 into 1 by 2 into 50 by 1000 into 200 into 200. So basically we got how much can we cut here 102030 102030 okay 4050 2 1 ja 2 it got cancelled, so 2 5 ja 2 5 ja 10, so this is your 100 okay, it's a 100 joule. Now final kinetic energy is equal to what? 1 by 2 into half m v square. So basically how you will get the answer final kinetic energy, how I will get the answer, v square is equal to 100 into 2 divided by mass. So as we know that mass of the bullet is 100 into 2 divided by mass of the bullet is 50 by 1000 kg. So 50 into 1000 kg. So 52 ja So this will be 4000 is equal to V square. So V will be equal to 20 root 10 meter per second. So this is the final velocity. So I hope you all have understood how to do this. Okay. So there is no use of a thickness of the plywood and all. So they are telling only that it is 10% of the initial kinetic energy. Now we will do for a work done by a variable force. See, it is always not like that force will be at a constant rate. For example, I will show with some demonstration. Okay. Let us consider an object is here and a force applied to an object is here 10 Newton, and after some time it increases to 20 Newton when its displacement is S1, and after some time it decreases to 5 Newton when it displacement is S2. So as we know that their force is also variable, force is variable variable with displacement. So it is very difficult by using formula of work done like F into D into cos theta. So directly if you multiply with force, so which type of force I should take, 10, 20 or 5? So there are lots of problem in this. So if there will be a case of a variable force, then what we need to do, we what we need to do, we what we need to do, if there is a case of a variable force, then what we have to do? For example, if I will draw and represent the force and displacement graph. So this is a displacement and this is a force. So force may vary like this. Force may vary like this. Okay. So as we know that force is every time for every displacement force is different. Okay. So if we collect all the small steps, then what will happen here? What will happen here? We can find an area. And what does the force and displacements area gives you? What does the force and displacement area gives you? Area of a force and displacement curve gives a work done. You will say how it is possible. See, let us consider if I will if I will find this area. So here it is a length into width. So length is what? What type of physical quantity I am talking about? It is your force, and width is what? X. So F into X is the area only. So area under force and displacement curve, force and displacement curve, displacement curve gives work done. Work done. Okay. I hope you all have understood the area under the force and displacement curve is work done. Okay. Now, if I will talk about the other aspects also, so we can tell here that if we want to find area, we can integrate this area. Okay, so I will use a different method to prove this how integration is useful to find out the work done. Okay, let us consider work energy theorem. Uh, Sorry. So integration by using integration you can find the area. Okay. Now one example I will show you with by one example how variable force with the help of variable force how work can be done. A woman pushes a truck on the railway platform. A woman pushes a truck on a railway platform which has a rough surface. She applies a 100 Newton over a distance of 10 meter. She applies a 100 Newton over a distance of 10 meter, and thereafter she gets progressively tired and her applied force reduces linearly with the distance to 50 Newton. The total distance through which the truck has been moved is 20 meter. Plot the force applied by the omen and the frictional force, which is 50 Newton versus displacement. So we have to plot a displacement and force graph. So let us consider this is a y-axis and this is a x-axis, and in the x-axis and y-axis we will give different things. For in example of x-axis, suppose this is a 1 meter, 2 meter, 3 meter, 4, 5, 6, 7, 8, 9, 10, 10, 11, 12. So lastly I have taken 10, 1, 2, 3, 4, 5. So this is a 5 meter, sorry, 5 meter. And if I will talk about the force, so suppose this is a 15 Newton force, this is 100 Newton force. Okay. Now, for a distance of 5 meter, how much C applies a force for a distance of a 5 meter? Let us see here. At a distance of 5 meter, how much how much force is being applied? 100 Newton. Okay. So can we draw the graph like this? So they C applied for up to 5 meter. C applied a force of 100 Newton, and after that what happens? After this, her force reduces to 50. Force reduces to 50. Sorry, C has applied for 10 meter, and after that her force reduces to 50 when it reaches to 20 meter. So her force decreases linearly when she got tired. So this is a force graph, force and displacement graph. This is a force and displacement graph. Now, friction force of 50 Newton is acting. So, as we know that friction force is always acting at a constantly because the object is moving. So, let us consider this is a minus 50 Newton and it is your friction force. It is a friction force. Friction force. So, friction force will always act constantly here, like until there. Okay. So, if you want to we want to find work done by Omen. So it can be written as area under curve area under curve of applied force by Omen. So this is force applied by Omen. This is a force applied by Omen, right? Then applied by Omen. So work done will be what? So work done will be this area, okay? And if you want to find this area, so how I will find this area? So can we tell here there is a rectangle and there is a triangle, trapezium. So force applied by the Omen will be equal to area of rectangle. Let us consider O, A, B, C, D, E. So it will be what? Area of rectangle AB DO. This is a DO plus area of trapezium BCED. BCED. So we will get cancel. So area under the curve of applied force. So how here we need to find the area under this curve. so that we will get work done. So you can find here area, total area. That is, if I will do nomenclature, so it is your O, this is your B A, this is B, this is C, this is D, this is E. So total work done will be equal to area under the curve of the applied force, that is equal to area of rectangle ABEO plus area of trapezium BCDE. So this will be base into height. So how much it is? Its base into height. So this base is how much? 10. Height is how much? 100. So 10 into 100 plus area of this trapezium equal to 1 by 2 into sum of the parallel side. Sum of parallel side. So this is a parallel side. This is a parallel side. So this will be 100 plus 50 into height. Height is how much? This height is was 20 minus 10. So you can write here 10. So how much it is? 10 2 5 jar 10. Okay. So this will be how much? This will be 1000 plus this will be 1750. So this will be 1750 joule. So total work done by the omen is 1750. Now if I want to calculate, if I want to calculate work done due to frictional force, then how you will calculate work done due to frictional force? So how you will calculate? So this will be this is very simple. See, constant, it is a constant force only, and displacement is 20. So we can write here constant force of 50 Newton into displacement is 20. So this is your 1000 joule. I hope you all have understood. Now I will talk about the work energy theorem for a variable force. Work energy theorem for a variable force. So I need to prove that work energy theorem for a variable force. So let us consider an object is there. It has mass m and force is being applied F. So definitely its velocity is u. So it may changes v or may changes. So velocity is changing constantly. Velocity is changing constantly. And if v is changing, it means kinetic energy is changing. At, so can we write here kinetic energy is dk by dt? For small changes, I will talk about small changes. So small change in kinetic energy per unit time can be written as dk by dt. And if it is dk by dt, so can we write here d by dt into kinetic energy formula is 1 by 2 m v square. Now mass is since constant, so mass is out, 2 is out. So can we write here 2v, if I will differentiate it, so can we write here dv by dt? So as we know that dv by dt, so these two cancel. So as you know that dv by dt acceleration is equal to dv by dt. So we can put here ma into in place of dv by dt, I can put ma into velocity. Now can we write here velocity? Velocity, as we know that velocity v is velocity v is equal to dx by dt. So can we write here ma into dx by dt, and this is equal to dk by dt. Now if I will cut this dt cancel out and integrate both the side. Since ma is your force, so force we know that it is a variable, dx is dx and it is a dk. Integrate both the side, and if I integrate both the side, integrate both the side by putting limit, both side by putting limit. So if I will integrate dk and integrate f dx, so this is it start from initial kinetic energy to final kinetic energy, and it starts from initial distance I to final distance f. So it is your final kinetic energy minus initial kinetic energy, and this is the integration of f dx and xi to x final. So integration of f dx is only work done. Work done. So we have proved that change in kinetic energy is equal to work done, and this is what talking about work energy theorem. Work energy theorem. So this is the second technique, and where we can use a variable force also, and you will able to prove that work energy theorem is equal to change in kinetic energy. Work and change in kinetic energy is equal to work done. I hope you all have understood this, and we will meet in the next video, and be connected here so that you will get regular video of the class 11 now. Okay, thank you everyone.